In this video, we will discuss the difference between a photovoltaic cell, module, and array. We will focus on the taxonomy of photovoltaic technologies, so on the terms and definitions that differentiate cells from modules and arrays. We will also discuss and compare a number of different PV technologies. Let's start with the modularity of a PV panel. A typical monocrystalline silicon solar cell is shown here. A PV module is created by connecting many cells in a circuit. The module is usually framed in some glass and aluminum. If several PV modules are electrically connected and mounted on one single supporting structure, in other words, when they are mechanically linked, they form a solar panel. A photovoltaic array is the complete power generating unit, consisting of any number of PV modules and panels that are mechanically independent. Apart from the mechanical connection, panels also need to be electrically linked through cables. Multiple panels that are electrically connected are called a string. The panels in a string are usually connected in series to obtain a desired output voltage. When two or more strings are connected in parallel, they again form an array. By connecting multiple strings in parallel, the output current of the PV array is increased. There are different technologies available for designing a PV system, each with their advantages and drawbacks. In general, these technologies can be found on the market today. The most common PV module technology is based on crystalline silicon wafers solar cells. These modules are rigid and usually framed with glass and aluminum. Lately, boosted by wafers thinner than 180 microns, bendable modules based on foil-to-foil encapsulation have appeared in the market. There are also a variety of thin film technologies, such as those based on thin film silicon, CIGS, cadmium telluride, and absorbing alloys belonging to the 3-5 groups like gallium arsenide. The last is generally used in concentrator PV and in space applications. These technologies can be produced on both rigid and flexible substrates. There are also some organic PV technologies based on dye-sensitized solar cells that can be made semi-transparent. Producing thin film technologies on flexible substrates has some advantages. For one, they are lightweight and can therefore be used on areas with a low weight-bearing capacity. The flexible substrates also do not require a mounting structure, which reduces the balance of system and installation costs. Another advantage is that the modules can be integrated into roof tiles and other building components, as shown here. Remember that for designing a PV system, the third step is selecting the PV modules. The question for an engineer is how to make this choice, since there is no straightforward way for choosing this or that technology. Currently, crystalline silicon-based modules are dominating the market because of the relatively low price and good yield. In general, however, the choice will depend on criteria like the price, conversion efficiency, available space, and also aesthetics. Indeed, if your rooftop is curved, a flexible solution might be preferable. Also, an all-black system or building integrating system is generally preferred by the customer because they are less visible than the blue-colored solar panels. If you have a relatively large area available, you might choose a cheaper technology with a lower conversion efficiency. In that respect, a rule of thumb is usually employed by companies that install PV systems is that when the price per square meter of a module increases by 20%, then the yield per square meter should increase by 8%. Now, let's take a look at the warranties and the lifetime of the different technologies. We already discussed that each brand has its own warranty strategy, as indicated on the datasheet. Usually, lifetimes and warranties of wafer-based silicon PV modules are well over 20 years and are limited by the robustness and encapsulation. Let's look at an example of the output warranty of crystalline silicon modules. A first strategy is a standard two-step warranty. For the first 10 years, the company ensures 90% of the maximum power point at standard test conditions. For the following 20 years, an output of 80% is warranted. The second warranty approach uses a different strategy, assuming a linear performance decrease over the lifetime of the PV panels. This means that the warranty performance is higher at any point in time, which is beneficial for the customer. Of course, these values underestimate the actual power output and serve only to convince the customer of a minimum warranted performance. Nowadays, the linear warranty is becoming more and more the standard. We can consider the output warranty of the four main technologies that are on the market now. That of cadmium telluride modules is similar to that of crystalline silicon. Thin film silicon modules on glass substrates are different, however, since amorphous silicon suffers from light-induced degradation. The performance of thin film silicon stabilizes after an initial period of degradation, and the thin film silicon modules therefore have a warranty minimum power output. The output warranty is again about 90% for the first 10 years and 80% after that of the stabilized efficiency. Different companies means different warranty strategies. Here we see a three-step warranty for flexible thin film silicon modules. The warranted output decreases from 92% for the first decade to 84% for the second decade and finally 80% for the final years of the warranty. Let's summarize. We started by defining the difference between cell, module, panel, and array. We then discussed and compared the photovoltaic technologies available in the market. Finally, we looked into the warranty strategies employed for PV modules. In the next video, we will find out layer by layer how a crystalline silicon PV module is fabricated.